So, welcome back. So, now we will start discussing about the field techniques and the lab techniques, what we need to do for mapping active faults, and further how we will be doing the excavation of trenches to identify different events preserved in sediment succession. So, lab and field techniques in active fault mapping and paleoseismic studies. So, we basically what has been shown here, that we use satellite data interpretation and then go into the field, try to identify the features, those are the fault scarps, and also we do some geophysical techniques to identify the near surface deformation to some extent, but we won't be able to go to greater depth because we usually use the GPR and all that, but of course you can go at the deeper depth using seismic reflections and all that. So, let us look at what are the different parameters and different techniques we are going to use to identify the remnants of paleo earthquakes mainly. So, as we have discussed about the primary and secondary structures, we have now the primary and secondary evidence of the paleo earthquakes. So, primary evidence are those produced by tectonic deformation during co-seismic slip. So, co-seismic is at the time of deformation, a slip along the fault during earthquake, and the features which usually we will come across are the fault scarps, folds, colluvial wedges, folded stratas, etc. And this is on fault. So, this is near the fault, and off fault what you will see is the tilted surfaces, uplifted and round shorelines, uplifted terraces along the river valleys and unconformities, and also you will see off fault the secondary evidence is the tsunami, but this can be also considered as a primary one, because this helps us in understanding that what type of earthquake it resulted into the tsunami, and mainly in the subduction zone regions. So, secondary evidence are those produced by seismic shaking during earthquake. So, these are all what includes on fault. You will see liquefaction, sand blows mainly, fissures develop on the surfaces. So, this I was talking about, I'll talk in detail about the sand blows, but the fissures which I have shown in a couple of slides when we are talking about 1995 Kobe earthquake, and then landslide, lateral spreading, sediment compaction, etc. Off fault, here you will see softer sediment deformation, seismites. So, you can also have liquefaction on fault as well as off fault, and then such deformational evidence of the deformational structures on soft sediments, mainly the alluvium, then those are termed as seismites. So, what you will have the convolute beds, sand dikes, turbidites in the areas where you are having the water bodies, mainly in the marine setting, rapid sedimentation because of the ground shaking, shifting or transportation of huge boulders. This you will be able to see when you are having along the slope of any region, or you will also see the transportation of huge boulders which are related to tsunamis. So, we will keep in mind when we are talking about the on fault and off fault evidence, and whether they are secondary or primary signatures. So, in detail, if you look at the hierarchical classification of paleo seismic evidence, so we have one genesis, then you have location, timing, and what will be the geomorphic expression, and what you will see in the stratigraphy. So, for us what we are doing is mainly we are talking about the geomorphology, that is the expression on the surface, and the signatures which are preserved in the stratigraphic sequence. So, and further we have abundance of similar non-seismic features, then you have again the same, we are talking about that what are those non-seismic features, and that those are, so these are, you are talking about the primary, and briefly I have shown you in the first slide, and then you are having the secondary on fault as well as off fault. So coming to this on fault, instantaneous co-seismic, then you will have fault scarps, fissures, folds, mole tracks, pressure edges, etc. That will be your geomorphic expression, whereas in case of your stratigraphy one, you will have faulted strata. So displacement will be evident when you are looking at in the section and in the sediment succession, and folded stratas you will have unconformities or discontinuities. So this part is your cross-cutting relationship between the different layers. Then coming to the post-seismic, that is your delayed after the seismic event, then after slip contributes to feature at left. So they are like after slip features, and then you are having colluvial apron. So this is related to the erosion, which will modify the fault scarps or fissures or folds or mole tracks. Then the stratigraphic expression will be your scarp derived colluvial wedge, fissure fills, and etc. This will be after the, so whatever the fissures which are been formed, which will be covered by the next sedimentation, and that what you see is the delayed response. Then coming to the off fault, so these are the signatures, that is you are having primary and on fault, whereas this one is your off fault, and again what you see is the off fault instantaneous during the co-seismic. So now what we are looking here is that we are near the fault and we are moving away from the fault. So what are the signatures you will see during the earthquake, when the earthquake is occurring, then you are close to the fault and away from the fault. So away from the fault you will see tilted surfaces, uplift shorelines, subsided shorelines, etc. So this will be in the coastal region. Of course you will also see but in close to the on fault you will come across the uplifted terraces and all that. And then delayed response, very much similar to what we were looking at the on the on fault. This is what we will see. Off fault will be tectonic alluvial terraces, because delayed response will result into the erosion and the incision of the channels, which will result into the formation of terraces. So this will be a long term after the event, okay, after the seismic event, that is in co-seismic one, after SIP contribution to the features at the left. So you are having the modification of similar features which are been formed will be modified because of the delayed response, that is your due to erosion, and to some extent you may come across the elastic rebound phenomena. Then coming to the stratigraphy one, you will have off fault, then you have tsunami deposits. Of course the tsunami deposit, to some extent we consider that as an the primary signature, but since it is a secondary phenomena associated with the earthquake, we may consider this as an tsunami deposit as an off fault, because you will find the tsunami deposits away from the displacement of the fault in the subduction zones. So tsunami deposits and erosion unconformities caused by tsunami, you will see, because the tsunami waves are very powerful and will result into the very sharp unconformity with respect to the underlying sediment succession. Then delayed response, you will again have the erosional unconformity and deposition induced by uplift, subsidence, or due to tilting of the surfaces. So erosional unconformity will be the basic signature which you can identify, and this could be related to the delayed response of that is post seismic activity. Then coming to the non-seismic one, okay. So we will have very few signatures here, very few, some we will see, and very common in the delayed response. Okay. Then coming to the further here, we have the secondary. Those are created by seismic shaking. So mainly we are talking about the secondary features, and this we were talking about the primary one. So on fault secondary features, again because of the co-seismics, that is during the earthquake, you will see those are related to your strong ground shaking. So you will have sand blows. So this is a liquefaction. You will have landslides in the hilly terrain because of strong ground shaking, lateral spreading because of the loss of shear strength of the material in the fault zone, disturbed trees and tree thrown craters. Okay. So you will be basically looking at the uprooted trees in such cases during the co-seismic, and this all are your on fault secondary. And then you have delayed response, retrogressive landslides originated in the fault zone. So you will have this could be because the material which is sitting on the slope will definitely because of the strong ground shaking will lose out their shear strength and result into the delayed response to the seismic event, and you will have the landslides which are originated in the faulted region, that is on fault signatures. Off fault, again coming to the instantaneous, you will have sand blows, landslide, lateral spreads beyond. So depending on that what was the magnitude of an earthquake, this features you will come across. For example, I was talking in one of my lecture that MW 7.6 Bhuj earthquake, the secondary effect was observed like about 300 kilometers away from the epicentral area. So again you have uprooted trees, fissures, like Shakun Chen. This is the part of the very much similar to the landslide, but usually what we see is that if you are having this sloping surface, then the landslide will occur here. Okay, but this one usually what is been seen is something like this. So this portion has been slipped down, and because of this is a secondary feature, and such features are been termed as Shakun Jen. Okay, and then you have subsidence from the sediment compaction. This will be again the delayed co-seismic, but you will have off fault, and the delayed response is again the landslide beyond the fault zone area. So there are many common features which you will find in different type of deformation, hence they have been kept as common. But as we learn more about that, we will have fault scarp mainly in the thrust environment, but we will see along with the fault scarp we will see lateral displacement of the landforms, including the streams or the channels, river channels in case of the strike slip one. And of course the mole tracks will also be seen in the strike slip and pressure edges, formation of pressure edges along the thing. And in all cases you will see the displaced stratas or faulted, that is faulted, folded in case of the compressional tectonic environment and strike slip tectonic environment. And in all the environments, like three environments which we are talking, strike slip, normal, and that is extensional and compressional, will see unconformities or discontinuities between the stratas. So basically discontinuities, what we are looking at is that we have the horizontal surfaces, and if they are faulted, for example, then this will mark the discontinuity between the stratas. Further, the stratigraphic signature, in case of your non-seismic features, you will have sand dikes, then you have sills, soft sediment deformation, and landslide at the toe of the thrust. Then you have sediment deposited from retrogressive landslide, and further if you move away, that is on off fault, then you have sand dikes, field craters, soft sediment deformation, turbidites and all that. And delayed features, you will have the so this is co-seismic and these are the delayed post-seismic. So erosion and deposition, change in the sedimentation rate, because the deformation will trigger because the land level has changed. So this will trigger either into erosion or deposition in the area, depending on what type of movement, whether it is an uplift or it is you are having subsidence. Then the gradation and degradation of the sediments will respond to the tectonic events. And we will have landslides or surface features such as fissures, lateral spread, sand blows. So these are all the post seismic signatures you will come across in as stratigraphic expressions. Now in areas where we clearly see the on fault deformation, okay, that is in co-seismic features. If we are able to see co-seismic deformational features, then we will be able to easily pick up this one, and we will be able to mark the active faults and all that. But a regional scale, if you look at, then we will have to look at that what was the effect of that deformation on a larger scale, okay, which is away from the fault. And if suppose we are having the blind earthquake or on a blind fault, then we may not come across the features which are been listed here. In that case, we usually take into consideration the secondary features, which will help us in identifying the tectonic event. So in most of the areas where we have like even away from the fault, and we try to look at that whether the area was been affected by any earthquake during any earthquake by liquefaction. Okay. So lab and field technique in active fault and paleoseismic studies. So paleoseismic field investigation, what we usually do is that the paleoseismic events can be studied by landform analysis or stratigraphic expression. So these are the two most important parameters which we are going to emphasize for identifying the tectonic deformation. Now in case of for example, if you are looking at on the earth surface, that is continents, then we will be able to identify both, and that is your in stratigraphy as well as on the surface, okay, that is landforms. But in case of the subduction zone earthquakes, we won't be able to see the faults or the deformation which has occurred along the trench area, but near to the coastal regions, okay, we'll be able to pick up both the land level change as well as the sediment record. So mostly we try to look at both in most of the cases. So it is essential to look at the stratigraphic as well as the expressions which are preserved in landforms. Sequence of investigation initiates from regional scale, local scale, and site scale. This we have already talked about, that we looked at. Either you can say the global one, then coming to the regional and the local or site specific scale. You need to do investigation. Often requires trenching, albeit an important one. Data provides magnitude of hidden earthquakes and recurrence. So this is important for the seismic hazard assessment, that we need to have the magnitude of earthquake and the recurrence at what will be the next when will be the next event and what will be the magnitude. Careful geomorphic studies are required before trench excavation, that is proper establishment of quaternary stratigraphy of the landforms. So as we have been talking right from the beginning, that if you are having an active fault, then it has moved number of times and multiple earthquakes have occurred on that particular fault. So that means that the landscape has preserved the past earthquake events. So and whenever there is an earthquake, that doesn't mean that no landforms in future will form. So new landforms will come up. So what we would like to do in this exercise is we need to reconstruct first the total geomorphic, that is landform stratigraphy, in terms of which landforms are older and which are younger, and that will also tell you that if the older landforms along with the younger ones are displaced, then we can easily we can quickly make a decision that this fault has remained active since past, okay, where the older landforms are also displaced, whereas the younger landforms are also displaced. Of course, the amount of displacement on surface as well as in the stratigraphic section will not be the same, because the older one will show cumulative displacement, whereas the younger one will show the most recent event when they got displaced. Okay. So, you will need to establish the quaternary stratigraphy of the landforms as what we do in case of the sediment stratigraphy. So, first step what we do is the identification of the area, and then any particular area. So, we are moving from a regional or global to regional and to a site specific one. Okay. So, if we have to take into consideration the local site or the site at the local scale of our interest, then first of all the first step we will do is that we will look for the historical data, if any, in that of that area, and then we will have the broad understanding of geological structure. So, we will also consider here the global tectonics. Okay. So, here what we have discussed about the plate tectonics and all that. So, we will take into consideration that in that, and then we will look at the geological structure. So, we are talking about the regional tectonics. So, this will help us in understanding that what type of deformation one can expect based on the global tectonics. Then regional and site specific studies we will take, and we will do detailed geomorphic mapping using high resolution satellite data, and this what I was emphasizing in the previous lectures. And if we are having the stereo vision photographs, then this will help us in identification of active fault scarps, because in this will help you in viewing the whole area in 3 dimension. So, this exercise we will give a lecture on this, that how you will prepare the anaglyph and try to see the satellite photos in 3 dimension, and the terrain you can even use that data to generate the digital elevation model. And after doing the detailed studies, that is identification of active fault scarp and field mapping, then we will go for trenching, identification of trenching site. And for when we are doing this, that is the identification of the trenching site, we will take into consideration the landform stratigraphy. Because we would not like to excavate the older landforms. Okay. So, we will look for the younger displaced landforms. So, for this we need to have the landform stratigraphy of quaternary landforms, and the youngest displaced landform will be the target for the trench site. Okay. So, this you should remember. So, trenching to identify the pattern of deformation and past earthquakes. So, what type of deformation has been seen? Of course, based on this understanding that the global and regional and the geological structures and the landforms, to some extent you will be able to understand that what will be the pattern of deformation, either it is in reverse fault or thrust fault or strike slip fault. But along with this, the trenching will help you in identifying the signatures of the past earthquakes. So, now we are getting into the stratigraphy here. So, this what we were talking about, the landforms and all that, is your geomorphology. Then further detailed mapping of exposed trench walls. So, we will do logging and mapping of detail, and this will help us in identifying the cross cutting relationship between the sediment layers, and that will help us in identifying the number of events. Identification of event horizons plus the number of events. This we will do will be able to do when we are doing detailed logging of the trench exposed trench walls. Dating of events, upper and lower bound we will try to collect, and then that will help us in identifying the event when exactly it took place. Prepare a chronological chronology of the events. So, this finally will help us in identifying the slip rates also. Okay. So, just about the event horizon, if I have to just explain here, I will just put that. Suppose you are having an pre-existing fault scarp. For example, you have identified so this is the topmost surface which remained exposed before any particular event. Okay. So, suppose this you are having this layer over here, and then the rest of the layers were displaced. Okay. So, you have this unit was displaced, and this was been capped by this. Now, during the next earthquake, suppose for example, if you are taking the next earthquake, if you are having the displacement, then you have the displacement of this unit. For example, I am just putting in sketch here. And this also is displaced. So, what you have is this is your event horizon during the next earthquake. So, this is your during this that is the next earthquake, then this one, then this will become your event horizon. So, how many times these units have been displaced? Now, on that basis you will talk about the slip rate and the number of events basically, and finally you can talk about the slip rate also, that what was the amount of slip, or you can talk in terms of the average slip during one single event. So, using high resolution satellite photos, and these are what we say that this is one of the best photographs which are available, at least for the Indian terrain. We have these are the photographs taken by Corona satellite photo way back in 1960s, and we have this with the stereo vision. So, with this I'll stop here, and we'll continue in the next lecture and talk more in detail about the satellite photo interpretation and associated landforms. So, I'll show you some examples based on the photo interpretations and what we have done in field, and what all mapping tools we will use for collecting the data. Thank you so much.